but when you compare the order at which two sequences approach 0, using the L'Hopital limit comparison test, you take one sequence and the other sequence and you divide them, so you form the ratio an divided by bn. In the examples we saw yesterday, and in some of the examples that you did today, you had examples where you took this quotient and you took the limit of that quotient and you got an answer which was finite and non-zero. So that answer might have been 1, it might have been 3, it might be negative 17, whatever. It's finite and non-zero. So what conclusion did you make in that case? If this quotient's limit is finite and non-zero, what does that mean about the orders at which those sequences approach 0? Which is winning the race to 0, an or bn?
It's a tie.
It's a tie. If this limit is finite and non-zero, it means that even though both the numerator and the denominator want to get to 0, it turns out that they both get there at the same time. So we see something not 0 show up in this limit. So when it's finite and non-zero, we judge the race to be a tie. And this is the best possible case for the limit comparison test, because it means that the series summation of an and the series summation of bn are always going to do the same thing. If one of them converges, then the other one converges. Because if one of them is racing to 0 fast enough that the series converges, then since they get to the finish line at the same time, the other one will also. And conversely, if one of them is too slow, in other words, not getting to 0 quickly enough in order to converge, then so is the other one. So this is the best possible case of the limit comparison test. That when the limit of the quotient is finite and non-zero, we can conclude that these two series converge and diverge together. If one does, then so does the other, no matter what. So this is the clean case. This is the one we talked about yesterday. But in your groups, you also saw some examples of the other cases in the limit comparison test, where the limit of the ratio turns out to either be 0 or possibly to be infinity. And my advice to your groups when this happened today is that if you got a limit of 0, for instance, to think of that 0 as being 0 over 1. And when you think of it as 0 over 1, then you look back at your fraction and ask, well, what did the numerator and the denominator want? They wanted to get to 0. But here, one of them got what it wanted, and the other one did not. The numerator, in this case, ended up getting to 0 before the numerator did. The denominator, sorry, before the denominator did. So in this case, which has approached 0 at a faster order, an or bn? An. So we would say that the an wins the race if this quotient ends up tending to 0 as n goes to infinity. So what does that mean about the convergence or divergence of ans and the bn's? An converges, but only if what? Only if bn converges. So let's get that in here. The summation of an converges if the summation of bn converges. Because in that case, we would say that the bn's, the hare in this race here, is still, even though it's getting beat out by the tortoise here, it's still getting to 0 fast enough to converge. And if the ANs are getting there even faster, then so much the better. In other words, we're saying that the turtle's plane is making a smoother landing than the rabbit's plane in this example. And because the rabbit's plane is already landing smoothly, it's not crashing, the series is converging, and the turtle's plane is even smoother. Therefore, the ANs converge. But it's a very touchy thing, because if we don't know that the BNs converge, for instance, if the rabbit is running too slow, then we can say nothing. Then this comparison doesn't tell us anything about AN. But again, my hint in how to tease that all out is to write 0, when you get that limit of 0, rewrite it as the fraction 0 over 1, so that you can make it obvious which one of these two sequences has gotten to 0 at a higher order. So what happens with infinity? If the limit of this quotient is infinite, write infinity as 1 over 0 instead of 0 over 1. And make the conclusion that that must mean that the denominator has won the race to 0. Therefore, the BNs are getting to 0 at a higher order than the ANs. So now what conclusion can we make about the series summation of an? If the b of n's diverge, so in other words, if the turtle is too slow, and our rabbit is even slower, then if the summation of bn's diverge, then so does the summation of an's. So the series of an's diverge if the summation of the bn's diverge. So both of these cases, where the limit of the quotient is 0 and where the limit of the quotient is infinity, are tricky because they only work in one direction. When the limit is 0, that only tells us that the an's converge if the bn's converge. When the limit of the quotient is infinity, it only tells us that the an's diverge if the bn's diverge. So what you're always shooting for is to try to get the first thing to happen, because the first thing is the easiest. Because then whatever an does, bn does, when they tie, when they get to 0 at the same order. But because that doesn't always happen, you should make sure you're familiar with these other two cases as well for what happens in the limit comparison test when the limit of the quotient is 0, and so the numerator gets to 0 at a higher order than the denominator, or when the limit of the quotient is infinity, in which case the denominator gets to 0 at a higher order than the numerator. But always thinking of it as a race to 0, and L'Hopital is our referee on who wins this race, can help to keep straight exactly what conclusion you're supposed to draw from these applications of the limit comparison test.